Okay, welcome. And today we're going to start our first lecture on Chapter 1, Problem Solving and Critical Thinking. So welcome to Math 101, Quantitative Literacy. And so here we go. So the first section, this is the only section we're going to cover in this chapter. So inductive, and it's going to be about inductive and deductive reasoning. And inductive and deductive reasoning are the two branches of reason that we as human beings use. And in chapter 3, we're going to delve into more of a deductive reasoning, but it starts with like a bird's eye view of reasoning. And in fact, the idea of right reasoning. How do we reason well? And so this is where people like Socrates comes in, Plato and things like that. Okay, so, or if you even want to talk about Sherlock Holmes, who was a great master in inductive and deductive reasoning. Okay, so here are the objectives, right, to understand these two types of reasoning. So now inductive reasoning is the process of arriving at a general conclusion based on observations of specific examples. Okay, so what does that mean? It means that I want to take something I see, maybe a pattern or maybe a data set as a statistician, and a sample set, and I take these observations, these examples, and I say, okay, well, because I'm seeing this pattern or because I have this data set, I want to make a general conclusion about all things or all situations like this, okay, or how does the pattern continues, things like that. So the definitions we're going to start with is the idea of a conjecture hypothesis. Okay, conjecture is something that we assume to be true. Okay, it's not proven. It's something that we think is true. We assume it's true, but it's not proven to actually be true. A hypothesis is also the same sort of thing. Conjecture hypothesis you can look at a hypothesis the same way. It's something that we assume to be true. It's a claim that we make that we believe is true, but is not supported yet by any kind of data or empirical evidence. Okay, so the conclusion formed as a result of inductive reasoning, which may or may not be true. Okay, so that's the definition. Now, a counterexample is a case in which the conjecture is not true. So if we want to prove a conjecture hypothesis to be false, the easiest way is come up with a counterexample, an example of where it doesn't hold, and you're done. The conjecture is false, right? So if I say all cats are brown, right? I believe all cats are brown. Well, all I have to do is find one cat that's not brown, and my conjecture is false, right? So I make a conjecture that way. So that's a simple one. So now we're going to talk about strong inductive arguments. Now here's the thing: when we talk about inductive argument or inductive reasoning are either strong or weak based on the logic or the reasons that support the argument. Okay. So in this example here, it says in a random sample of 380,000 freshmen at 772 four-year colleges, 25% said they frequently came to class without completing readings or assignments. We can conclude that there is a 95% probability that between 24.84% and 25.25% of the college freshmen frequently come to class unprepared. Okay, so is that a strong inductive reason? Okay, so in this case here, yes. Okay, this is based on statistics. Okay, so if you have a good random sample, right? It says in a random sample, right? So This is called random sampling, right? So if you have a good random sampling, which we're going to discuss in chapter 12, then each member of the group has an equal chance of being chosen, okay, if it's a random sample and it's unbiased. We can make prediction based on a random sample of the entire population. So we take a sample, this is a very large sample of freshmen, and based on the sample, we found that 25% of them said that they come to class basically unprepared. Okay, and then we could say, okay, well, with a certain probability, with a certain confidence of 95%, we can say, hey, then we would say that somewhere between 24.84% and 25.25% of all college freshmen come to class unprepared. So this is an example of inductive reasoning, and it's strong because it's based on a good large random sample of the population. Okay, and so we're taking that sample and we're saying, okay, we're basically making a inference. We're saying, hey, we can apply this to the entire population of freshmen. Okay. Weak inductive argument. Okay, so in this example, it says men have difficulty expressing their feelings. Neither my dad nor my boyfriend ever cried in front of me. This conclusion, so it says, okay, so what's the conclusion here? The conclusion in this case is the first statement. So now you got to understand, sometimes the conclusion comes at the beginning of a paragraph, and that's the thing about English, right? So what is the conclusion here? Well, the conclusion is that men have difficulty expressing their feelings. Why? Well, here's the support sheet that this person gives. Neither my dad nor my boyfriend ever cried in front of me. So in this case, she had used two people, two examples, right? So based on these two examples, she's making the conclusion that all men have difficulty expressing their feelings. Well, this is not a strong inductive argument because it's only based on a sample size of two people, right? Very small sample size, right? Two examples, okay? So that's one issue, okay? So this sample is neither random, that's one, right? Your dad and your boyfriend, so definitely not a random sample. And it's not a representative sample because it's your boyfriend and your dad probably don't represent the entire population of men, and probably not even accurately, okay? Okay, so here's another use of inductive reasoning. So it says, we have a pattern here. It says, first, we want to identify the pattern in each list of numbers, and then we want to use this pattern to find the next number. So in this number, so here, look at the pattern. So we have 3, 12, 21. So what's going on here? So 3 to 12, right? And then 12 to 21, and then 21 to 30. So how do we get to 12? You have to add 9, right? And then to get to 21, you added 9 again. And then 30, added 9. So it looks like we're adding 9 every single time. So based on this pattern of adding 9 every single time, what's going to be the answer, the next number? 48. So we have a common difference, right? So there's a common difference between each one of the two additions. Now it could be addition or it could be subtraction in some cases, but we see this common difference between each successive number, each sequence, right? Each two numbers. And so if we continue the pattern, the next number should be 48. Okay, now what about this one? Well, here, these are going up pretty darn fast. So addition probably is not going on here. So let's try multiplication. Well, what are we multiplying by to go from 3 to 12? 4. What are we multiplying to go from 12 to 48? 4. I bet if we take 4 times 48, we're going to get 192. Well, guess what? 4 times 4 times 40 is 160. 4 times 8 is 32. 160 plus 32 is 192. Yep. And if you take 4 times 192, you're going to get 768. So what is going to be the next number? Well, you're going to multiply 4 by this number and see what we get. So in this case here, 4 times 7 is 28, so that's 2800. 4 times 6 is 24, so that's going to be 3000 what? 40? Right? So 2800 plus 240 is 3040, plus another 32 gives you 3000 what? 72. And we get 3072. All right, good. So now let's go to this one. Ooh, what's going on here? So it says, what comes next in the list of numbers? Now this is kind of strange because we have 2 ones here. So it goes 1 and then 1. Well, how do we go from 1, 1, and then 2? And then it goes 3, 5, 8. Well, this is a difference of 0. This is a difference of 1. This is a difference of 1. Then it's 2 and 3. So it doesn't seem like there's not a common difference. There's no common multiple, right? So what's going on here? Well, this is a very special sequence of numbers. And if you notice that if you add these 2 numbers, you get the third number, 2. And if you add these 2 numbers, you get the fourth number, 3. If you add these 2, you get 5. Now you see the pattern. 3 plus 5 equals 8. 5 plus 8 equals 13. 8 plus 13 equals 21. So now, what is the next number? Well, add these 2 and you get what? 34. And this is a special sequence called the Fibonacci sequence. This occurs so often in nature and in sciences that we had to give it a name by the famous Italian mathematician Fibonacci. And the answer is 34. Now, here's another one. So inductive reasoning can also lead to more than one solution. So here, we've got 2, 4. Well, in this case here, what's the next number? Well, it could be 6 if it's a common difference of 2, or it could be 8 if we're talking about a common multiple of 2. So we're going to need more information to decide. Okay. Also here, we have this famous pattern here. One person could look at it and see a white vase, a white goblet or cup. Another person could look at this and look at the 2 black figures and see it's 2 people facing each other. So again, it depends on the person. So in these types of cases, inductive reasoning could lead you to more than one answer that is just as valid. So we would need more information. Okay. Now, what about figures? Well, look at this pattern. So here, notice what's going on here. It goes circle, square, circle, square. So what's the next figure going to look like? A circle. Right. I would guess the same thing. Now look at this pattern though. Here we've got 1 dot, 2 dots, 3 dots going in clockwise. So it starts 1. So it's going in the clockwise direction and increasing by 1 dot, 1, 2, 3. Then here now it looks like all the dots are moved 1 quadrant, if you will, counterclockwise. So now this dot went up here. Now it's going 1, 2, 3. Now on the next one, it goes to the next one counterclockwise. And then now it's down here. Now the next one is going to, if we keep the pattern, it should be not only a circle, but the dot is going to be in the rightmost quadrant. So it's actually going to repeat this symbol. So this one is going to go right here. And so this pattern is going to continue to repeat itself over and over again. And there you go. Now, deductive reasoning. Deductive reasoning is the process by which we go the opposite direction of inductive reasoning. So deductive reasoning is the process of proving a specific conclusion from one or more general statements that are assumed that may or may not be true. Okay, most cases were assumed to be true, or they are true. Okay, a conclusion that is proved to be true by deductive reasoning is called a theorem. Okay, that's called a theorem. Okay, in mathematics we deal with theorems all of the time. Okay, so deductive reasoning is the process of proving a specific conclusion from one or more general statements. For example, if I make the statement, all dogs, oh, let me see. All dogs are animals, and then I make the statement that Rex is a dog, therefore Rex is an animal is an example of using deductive reasoning. So I make two general statements, right? General statements that one is Rex is a dog. Well, that's more of a specific example. Or so I have a general statement. I say, hey, all dogs are animals. Hey, Rex is a dog. Therefore, Rex is an animal. Okay, so that would be an example of using general statements and coming to a specific conclusion. So here's an everyday situation. It says one player to another in Scrabble. You have to remove those 5 letters. You can't use Texas as a word. Right? So that's an example of deductive reasoning. Okay? You cannot use Texas as a word in Scrabble. Therefore, you have to remove those 5 letters from the Scrabble board. So the general statement is all proper names, right? All proper names are prohibited in Scrabble. Texas is a proper name. Therefore, Texas has to be is prohibited in Scrabble. Therefore, you must remove it from the board. So in colloquial, in English, this is how we talk. But the deductive reasoning that's going on, we would put it in this form because it's easier to see the argument. A lot of times, English is very messy, and like most languages, but English tends to be, has a lot of different wordings, a lot of different meanings, and so a lot of times we have to take something that's said in words and write it in this statement, where we have the general statements separated from the conclusion. And so this would be what we would call a deductive reasoning right here. Here's another type of inductive reasoning to find patterns. Okay, so we can use inductive and deductive reasoning in the same problem. Okay, so we select a number. So here's 4. We want to multiply the number by 6. Then we're going to add 8 to that product. Then we're going to divide the sum by 2, and then we're going to subtract 4 from the quotient. Okay, so this is our algorithm, if you will. Okay, so we're going to apply these rules to each one of these numbers. Notice that if I use 4, I multiply it by 6, I get 24. Then I'm going to add 8 to that product. So I'm going to add 8 to the 24 and get 32. Then I'm going to divide this divide this sum by 2 and I get 16. And then I'm going to subtract off 4 from the quotient, I get 12. So I started with 4, I ended up with 12. Now if I do the same thing with 7, I start with 7 and I end up with 21. Okay, so 4, I end up with 12. 7 gives me 21. You guys see the pattern yet? Well, let's do another one. 11, and I go through this algorithm, and I end up with 33. So now I get 4 gives me 12. 7 gives me 21. 11 gives me 33. Now do you see it? Well, what's going on? So I put an input in, and I get an output. So here it is. So now here is, right, the pattern that we're looking at, right? So let's look at what we're doing here. So we're using deductive reasoning, right? So we're going to using deductive reasoning, we're going to use n to represent any number, right? So what we're going to do is we're going to select a number, n, right? So here's the thing. So we start with inductive reasoning, right? Because we're starting with these patterns, right? So here's the pattern, right? So we're seeing a pattern here. Now we're going to say, okay, let's take a specific number, n, and see what we get. And so we're going to multiply it by 6, right? So we get 6n. Then we're going to add 8 to the product. So we're going to take 6n plus 8. Then we're going to take this sum and we're going to divide it by 2, right? Which then we can simplify to 6n over 2 plus 8 over 2, which gives us 3n plus 4. And then what we're going to do is we're going to subtract 4 from it, and we get 3n. So if we start with n, any number n, we end up with 3 times n. So does this agree with your hypothesis and with your inductive reasoning? So inductive reasoning told us, hey, it looks like every time I put in a number, 4, I get triple the number. 4, 3 times 4 is 12. 3 times 7 is 21. 3 times 11 is 33. So to prove, right, so that's inductive reasoning, right? So it may be strong inductive reasoning, but strong inductive reasoning isn't a proof. But if we want to prove it to be true, we have to use deductive reasoning. And so we pick any number. And if this works for any number, then we're done. So we use deductive reasoning. Okay, so now that's where we're at. So that's the end of 1.1. And so next time we're going to start chapter 3, which is going to be getting into logic. Okay, and logic, and we're going to start with more of deductive reasoning. That's where logic, but also logic comes into inductive reasoning also. But in this class, in chapter 3, we're going to stick with deductive reasoning for the most part. Okay, in inductive reasoning, we would have to talk about what makes a strong argument, and that we'd have to get into weak and strong arguments, and we'd have to talk about fallacies and cogent arguments. But we're not going to deal with it in this class. We're going to stick with deductive reasoning because it's more concrete. But most reasoning that's done is a combination of inductive and deductive reasoning. In fact, I would argue that probably the majority of reasoning that's done in most circles like politics and debates is inductive reasoning, I would say. But again, I might be wrong about that. Especially in statistics, that's where I would hang my hat. But anyway, next time we're going to talk about deductive reasoning, and we're going to get into logic. We're going to start with logical statements. We're going to talk about this idea of logic. What is logic? And we're going to go from there. But this ends chapter 1, section 1. And next time we're going to start chapter 3, and we're going to start with section 1. Until then, have a great day. And remember, practice this stuff. Come to class prepared. Make sure you watch these videos before class, because it's going to help you in class. Because when we get to class, that's where we're going to practice, and that's where the rubber meets the road. So make sure you take notes, make sure you write down your questions, and then come to class prepared to just dive right in and practice and work on homework, ask questions, because that's where the understanding is going to come in. Thank you, and I'll see you in class. Bye-bye.